which is that. I should be able to ping that from the world, and then I should be able to SSH in. It's not letting me. So what do we need to check? I'm getting IP connectivity. I'm getting response back from SSH.
Or security.
So we know that everything's making it there and back. It's just the password's not working. So there's a couple things I can check. My username, make sure it's created. With it's not because it's brand new, right? So I'm gonna go create username, CBO, password, ABC or secret. So that's not working yet. What else can I check?
You have to do the not logging locals at
In the line sections at the bottom, remember? With line console 0, line VTY. This is looking for a login out of the gate. The VTY is the SSH telnet connections. We have to change that to login local to go look at the usernames at the top. Just like the console 0, which I'm going to set. That's why I'm in here. And line VTY 0 through 15. Not capabilities. So now that should look a little bit cleaner. Here's my console. It's going to look for the username and password database. And then my line VTY section, which is SSH telnet. It's going to go look there as well. So now, ideally, that should let me know if I type the password in right. Yay. So everything looks like it's working. I don't have an enable password set, so I want to set that before I log out. Otherwise, I can't get back in. So let's go set enable secret. We'll say ABC123. And that's the wrong one. Okay. So I proved that I can log in, get myself enabled over SSH. Looks like it's okay. I'm safe to write the changes out in case the power goes out. I know I'm in a working state, right? You don't want to save things until you know you're able to get back in and finish your changes. If I had saved before I added the enable password and the power went out, I couldn't get back in and enable because there's no password set. Just going to throw an error. So you want to make sure you kind of check these little boxes off before you reboot it or the power goes out. Or you save it. But yeah. So just go through that on your own. Should be mostly what we just did. The copy is going to take the longest, so you can do all three of them. Just escape out of your 32, go to 31, do the next one, then go to 30, do the next one. Let them all load while you're in class. And then when you go back to it, you can just press enter and see if it's done. In case you have to log out of their R10 for some reason. So on this one it says make sure telnet is not responding. That one we just do with this transport input all. We go into line BTY 0 through 15 and say transport input. This tells us what protocols we want to allow people to get in on. We just want to say SSH only. If I didn't have that, then the telnet process is listening, and anybody in China or wherever, North Korea is going to be trying to get in and try to brute force my password, if you will. We don't want that. So.
Cassidy?
Yes.
Why does it keep breaking up your VTY from 0 to 4 and 15?
Those are just the default ranges. You can do different things for different ones. So you can say this one, these first 5 I want to allow SSH, these other ones I want to do something else. Okay. You can tell it when you log in which VTY you want to connect to. I just apply it to everything. I've never done anything separate. So that's that. If you got questions, please let me know. It's due next Monday night. I'll double check all the port assignments, yeah.
Is it show boot on 3750 and then show run on for the pass off, the before and after?
Let's see.
Are those the commands they want us to?
Show run config of all three devices. You do a show version before and after you reboot,
It shows.
then it'll show the actual version that you're running. So in this case, this one's running, let's copy this up here. And say this is before, then I copy the same thing after and see, oh, it's different now. To prove
Will
that I
that
actually
change
did
all
it.
your configs?
What was that?
Will that change all your configs, like the login local and?
No, it won't. If you're running a really old version, and then you try to write changes after you get the new one loaded, it'll say, hey, this is running a really old version, do you really want to overwrite this? And you say yes. That's fine. But none of you should have that issue. But all you really do is just copy here's what I was running before, here's what I'm running after, and that kind of shows me that you did that part. Yeah, so let's move on to other fun stuff. Let's see, Ethernet LANs. This was a nice one. So this is chapter 10. Now we're getting into VLANs layer 2 stuff. Hubs or peak signals. That means you have collisions because you only get half duplex. You're sharing 10 meg and it's shared, and daisy chaining sucks. So hubs were awesome, not really. Then we got bridges. They second collision domains. So you have everybody on this side of the bridge can collide on a hub, and everybody on this side can collide on a hub. The bridge is smart. He learns the MAC address and says, am I going to forward it or not forward it? So he can get double the bandwidth. He buffers frames until he can send, and increases bandwidth so each side can get their own 10 meg. So you get 10 meg over here, and one collision domain, 10 meg over here. Yay, it's really fun. So collision domains is a set of all areas in your network where packets could collide. Broadcast domain is what? We talked about this already, kind of.
That's to, the broadcast domain's the domain of when you send out the signal, hey, I'm looking for this IP.
When I'm sending a broadcast, who's going to get it? What's
Everyone.
encompassed in that broadcast domain? So when I send out, hey, I'm looking for Brad's MAC address, everybody in the same network gets that, and that's the broadcast domain. Let's see. So in this case, Larry sends out a packet, they all get it, it's that. In this case, when somebody sends a packet, you have a collision, and tears will ensue, and they'll have to retry over and over again. Let's go do this one. I have double. Okay. On a switch, we get 4 different collision domains because we're running full duplex. We're not going to collide because we can transmit and receive at the same times. This guy can talk at the same time as this guy. But the switch is smart. He buffers stuff in his memory. Think of him just a bridge that bridges 2 different ports together when they need to talk. But he's smart and he bridges or he buffers things until he can transmit it to Fred, for instance. So each port on a switch is its own collision domain. So on a 24-port switch, you get 24 independent collision domains. Basically, you're only colliding with yourself. You're not really colliding with anybody. Each one is its own independent bridge, if you will. In this case, routers and bridges segment your collision domains and your switches. Yeah, so talked about that. Router stop broadcasts. When the router hears a broadcast, he's not going to forward it off to the next hop up the chain. He's going to keep it on the inside of that network. Your broadcasts don't leave your local LAN network. Bridges forward all of them. Broadcasts sent by device in one domain are not forwarded to devices in another broadcast. So each one of those different broadcast domains, let's say we have a CIT network and a science building network. Broadcasts here aren't going to make it over there because they're in 2 different broadcast domains. Smaller broadcast domains are better because we don't have as many people listening to all the broadcasts. Better security, better everything. So we try to keep our broadcast domains as small as we can so that not everybody in the world is hearing everything. Every time I want to talk to Brad, I have to say, hey Brad, I'm looking for Brad. And then everybody else in the whole campus might get it. That's kind of excess packets that we don't need to send all the way to Hurricane. So let's imagine these are all on one VLANs. All these guys, when he wants to talk to this guy, everybody else gets all those packets on the campus. Bad, right? Kind of see the problem? I don't know why. I already had that one. The book changed things up, so I was trying to go through and keep some old slides, so I have to redo things. Some of these are a lot duplicated. So we have two different broadcast domains. Let's say Science and CIT are on the different switches. Dino and Fred want to talk, and they're in their own broadcast domain, and Will and Betty, but that adds extra security or extra physical hardware. We can combine these broadcast domains into one device, but keep them separate, so that Wilma and Betty, her broadcast domains aren't going to be reached by Dino and Fred. And we do that with what are called VLANs. So instead of using two switches, we can do it all with one switch, put everybody on the same switch. So if Science and CIT were in the same building, they could all talk with their own little broadcast domains on the same switch, but we're not hearing the the Science building's broadcasts because of these cool, awesome VLANs. It gives us better security, smaller broadcasts, and smaller spanning tree protocols. So VLAN's kind of a crazy topic. Here's an example of a wireless provider in town. They had a bunch of towers all around southern Utah, and then they had a bunch of customers on each one of those towers. And then they put them all in the same broadcast domain. Do you see a problem with that?
Nope, not at all.
What's the problem, do you think?
There's a lot of extra.
So this guy up here says, hey, I need to talk to this guy right here. Everybody in the freaking world gets it. So imagine like 4,000 customers all hearing the same broadcast, just from one little tower up here in Enterprise. Not the best use of your network. So we segment these down by smaller broadcast domains, so that stuff down here doesn't have to be heard by people all over the freaking county. So what we do is we use the same switch. We're able to define VLAN, segment our VLANs out, so that Dino and Fred, even though they're on the same switch as Will and Betty, they're not hearing each other's broadcasts. Again, these are only two machines on each, but imagine if you're a campus and you have a big switch of 1,000 machines. You don't want all 1,000 people to hear everything else going on all the time. You want to break it down by departments or floors or printers and copiers get their own. So broadcast exists. They have a purpose, you can't get rid of them, but too many clog the pipes. That provider was having issues with voice traffic because they were having too many broadcast traffic, including all their networks, taking up all the airtime of their radios. So once we were able to limit that broadcast stuff down, their voice cleared up magically, because there weren't all these packets that everybody had to process every time. So VLANs are broadcast domains you create to minimize broadcasts, and routers don't forward LAN broadcasts, so they create separate broadcast domains on each interface. So let's see, design terms we talked about first. Access switches, they connect to end users. Distribution switches connect all the access switches together. And we have core switches. So access switches, I usually put those at the end of the closet at the hall. All the computers in the hall plug into it. Distribution switches, all those hall switches plug into a distribution switch. So like in campus, here in this building, they might have a bunch of different access switches for the lab machines or the different rooms. Those all probably plug into one or two distribution switches back here in Alan's little room. And then those all plug into a core switch somewhere back in the data center or on campus. So in this case, here's our access switches. They all plug into distributions with redundant paths and such. And then those plug into a core switch or something up here. I guess this is only 2 tiers. Full mesh with only 15 links. So if you have all these distribution switches around campus, you want to have a full mesh, you get a lot of different links, and that adds up cost and fiber ports and cabling and headaches. So here's, for instance, Hazy, here's Smith. We have 2 different distribution switches all trying to mesh with everybody else. Adds extra fiber and stuff we don't need to worry about. So that's what we had a core. We had a core that everybody talks to. And those are all meshed to each other instead of meshing between each other. So everybody meshes with the cores, and then the cores are kind of the guys that are in charge of everything. This is more or less how Alan has his set up. One on the north side of campus, one on the south, and away we go. He should come probably in November and give us a few little stuff like this to talk about. All right, Ethernet standards over time. Early 90s, we had 10 base T, then 100 meg, gig, 40 gig, 100 gig. So that's your standard. Speeds are going up. They actually have 25 gig now, just because 40 gigs aren't as common. It's cheaper to make the 25 gig ports. Physical layer stats, remember these 802.3 somethings are all Ethernets. And then the different names and speeds depending upon what those map to. So 802.3 BA is 100 gig over fiber. You don't really know much about this except 100 meg, base T, 3U. I don't even know if you even know these little letters for the Cisco CCNet, I can't remember. Anyway, so that's your physical layer standards. What link do you use? So if you're on here and it's like, hey, which link do I use between my core and my distribution? You have to figure out how far apart are your devices. Is it too far for copper? Too far for copper? What about fiber? How much bandwidth do you need between your two sites? And how much is it going to cost? And if you're Dixie, you have a limited budget, you just throw whatever you want at it. Right? Is that how it works? And also the cable. So if you don't have cable between here and Hazy, you want to hook up a 100 gig link, you're going to have problems. So you have to have cable, appropriate ports, appropriate optics on each side, and the fiber, and all that good stuff. So it all adds up. So remember, 100 base T goes only 100 meters, same thing with gig, and 10 gig copper. Multi-mode, 550 meters. Single mode could go a lot further because it's lasers. I think when they reran all the fiber on campus, they used single mode, whereas before they did multi-mode, which they were running into the distance limitations. That's chapter 10. That's in Norway. 1,400-year-old, or year 1,300 or 1,400, I think, so that's built. So 11's when we actually talk about VLANs more, which we got like 15 minutes, so we'll dive right in. LAN is all devices in the same broadcast domain. We group users by floors or departments, like people get put in the same VLAN. So in my office, I have all these cameras so I can watch Brad and Jeff while they're doing something that they should be doing at work. And I put all those cameras in their own VLAN. So they're not hearing broadcasts from the machines on the network. The wireless APs are on their own VLAN, so they're not hearing broadcasts from the cameras. Keeps your overhead low from the number of broadcasts, and the lowest spanning tree, bench security, we talked about that. And then we can separate our video and our voice traffic from the regular data traffic, so we can prioritize a different VLAN over another. So all my video, if I'm doing video over IP, we have some live video feeds. Those come in over a different VLAN, and they get different priority queues on the back end than just regular people watching Twitch. So same thing with voice. That should get a higher priority than Twitch streams, right? Should, but we'll see. And then we'll talk more about prioritization later. What was that?
So when you get an 800 down and 800 up, it doesn't matter.
Doesn't really matter too much.
No.
Yeah. But you want to make sure the voices are
Yeah.
in the queue quicker. All right, so with two switches, we talked about this. We do it with one switch, create different VLANs. We can link two switches together in the same VLAN. So these 2122 want to talk to 2324, but they're on different switches, so we can put them both, the port between the two switches in that VLAN 20. Same thing with these guys. They can talk to these guys because we have a port in VLAN 10. That kind of is okay, but let's say I have 20 VLANs. I don't want to have 20 different ports between each one of these switches for VLAN 10, 20, 30, 40, 50. That's crazy. So we have this cool thing called a trunk port that allows me to pass multiple VLANs across one cable. So I can pass VLAN 10 and 20 on one cable. So that these guys over here can talk to these guys in the same VLAN through one cable. And the switch knows that. He says, okay, this traffic coming in, this guy, we configure him for an access port. Access port means it's an end user port. They don't know anything about VLANs and don't really care. A trunk port is a port that knows everything about VLANs and cares about what VLAN number he's on. So on trunk ports, you tell him, I'm on VLAN 20 and I'm on VLAN 10. And on this side, you tell him, I'm on VLAN 20 and I'm on VLAN 10. On access ports, you just tell them the switch, hey, whenever stuff comes in, put them on this VLAN number 10. but the customer or this computer doesn't know anything about VLANs. So whenever traffic comes in, the switch says, oh, that's on VLAN 10, I'm gonna put the VLAN header in front of his packet, ship it off. This guy looks at it and says, oh, that's VLAN 10, I know that's going out this port. I'm gonna pull out the VLAN header because he's on an access port, and this guy gets the same packet as it came in. With Ethernet headers, we just put this little VLAN ID, which is 12 bits, so it can go up to 4096, if I remember right, or 95. It's part of the layer 2, it just sticks this in here, so the switch can learn the MAC address, or learn the VLANs, or assign them in the different VLANs so they can't talk to each other. So if you're on VLAN 10, when your packet comes in, the switch will put that in there automatically. When he leaves the switch to another access port, I'm talking to Brad, he's gonna pull this tag out of here and Brad gets it unmolested Ethernet frame. If I'm talking to another switch port or another trunk port on another switch, it's gonna keep that when it comes in and do what he has to do to it. So, untagged versus tagged. Tag is when we pass the VLAN, we put the VLAN number in there, we pass it off to another switch or somebody that knows about VLANs. If I'm doing, for instance, I have like a backup server, I want to put him on multiple different backup networks. Instead of having a different cable for each, my MySQL, my Postgres network, my router backup network, I put him on one cable and I can put him on a trunk port so that he can be configured for VLAN 10, 20, 30 on the actual server. That's a tag here, a trunk port. Untagging means that the computer that plugs in doesn't know anything about VLANs and he's not going to be configured for VLANs. The switch port adds that when the traffic comes in and takes off the VLAN when he sends it back to the end user. Access ports are the same thing as an untagged port. They're only in one network. They don't know anything about VLANs. And trunking is how more than one port could belong to multiple VLANs via VLAN tags. So, when this first came out in the late 80s, early 90s, Cisco came out with their own standard because it was awesome and nobody else had a standard, so they made their own called Inter-Switch Link. And we had to tell it what, or they told everyone in the world, hey, we're going to make our own standard. Then the IEEE came out with 802.1q, which is an open standard. And everybody can use it. We want to use this whenever we configure trunking protocols on our ports. For next week's assignment, we're going to actually configure our routers and our uplink ports to be VLAN trunks. So you can be passing VLANs from VMs that you can create back into your routers and stuff like that. So ISL versus 802.1q, we shortened that for .1q. On your 3750, you tell it what trunking protocol you want to use on the trunk port, whether you use an ISL or .1q. You're always going to use this 99.9% of the time. So use .1q when it comes to your trunk ports, which we'll go over as well later. So we can use, for the VLAN numbers 1 through 4094, because it's only 12 bits. So we pick a number between 1 and 4094 for VLAN and assign everybody on that port to that VLAN number, and they're all the same broadcast domain. Because it's not just easy to have one big range, Cisco splits them into two different ranges. You get the normal and extended. Normal is 1 to 1005, and extended is everything above 1005. Earlier switches didn't let you do extended ranges because they didn't have enough memory to do that high. So early like 2912 switches, which we had like 10 years ago, but all your switches will do the whole range, so you're good to go. It's just one CCNA question. VLAN ranges, normal and extended, what are they? So let's say I have a trunk port, passing VLANs between each side. So we got port A, port B, you want to pass. Those are being tagged, so they have the VLAN header in the packet every time. So everything going over is going to have a 10 or you can have a 20 in it. You can set up what's called a native VLAN port, so that anything that comes over without the VLAN it's gonna assume, I'm gonna put that in VLAN 30 if it's the native port. Just allows us to have another VLAN that's not tagged, that goes across the network. Reason you wanna do that, management VLANs on devices. Some devices, they'll pass VLANs just fine, but they don't have their management capabilities on VLAN tagging. So if I want to reach my switch here, or let's say I have a bridge here, there's a router. He'll pass stuff through just fine, but if I want to manage him, I have to put him on a native VLAN. We'll talk more about this later, but it just allows us to pass another VLAN through that's not tagged. So normally on a trunk port, everything is tagged, but you get one little extra thing called a native that lets you pass untagged. Both sides have to agree on what VLAN is the native untagged VLAN numbers, up to 30 on both sides. Otherwise, they throw errors and cry. All right. Confused yet? Oh. So because we're on a layer 2 switch, these guys want to talk to these guys because they're sharing files or whatever. We need some way of bridging the gap. What we do is we put a router on there. So Dino and Fred can talk to their default gateway, who's also connected to the Will and Betty VLAN 20 network, and they can route packets just fine. Note that we have two different cables here, all on the same switch, just one's on VLAN 10 and one's on VLAN 20. They created this cool little term called a router on a stick that allows us to use one port on a router. And we configure it for a trunk port, so we can pass VLAN 10 and VLAN 20 through the same cable. Just like we had two switches, instead of having two different cables, one for each VLAN, we would have one. Our router would just have one port for each, for the trunk. So Dino talks over the same cable that the router would talk to Bill or Wilma or Betty. So in this case, the router and the switch, they agree on which VLANs they're passing on this port. So they know I'm passing 10, I'm going to accept 10. On these ports, they're access ports, so they're untagged, which means the Dino just passes Ethernet frames without any VLAN numbers. And the switch, when he sends them back to Dino, he sends them without any VLAN numbers. Otherwise, Dino gets confused and throws away packets. So with a layer 3 switch, we combine this layer 3 functions into the switch itself. So we just put our gateways on our layer 3 switch. So our 3750 can now be the gateway for VLAN 10 and VLAN 20 without having to bounce through another device. So we kind of combine all the routing features that we would get down here back into our cool little layer 3 switch. So part of our assignment next week is we're going to have our routers. So you got your router 1, router 2. Those are both going to talk to your 3750. And he's going to be the gateway for your router number 1 and for your router number 2. He's going to route packets over to me. So right now, all of these guys are on the same VLAN. So this guy is on minus .131, .132, .133. He was like 129. They're on the same broadcast domain. We're going to break that up into smaller ones next week. Yeah. Questions?
So all the computers out here are plugged into a switch. That switch goes to a router.
Well, the switch, you're all plugged in the same switch. Those are all probably in one VLAN, but you're in an access port mode, which means you don't know anything about VLANs on these computers. But your switch that they plug into puts them in a VLAN once the packets come in. He says, oh, that's going to be on the lab VLAN number 6 or whatever. And then those talk to a router, wherever it is. And that's also in VLAN 6, because you have to be able to talk to the router. But yeah, so we'll go over more of this later. I mean, it's a big topic. We're going to go over it. So VLAN database on your switch. You can create VLANs because you need to be able to manage them and create them and delete them and go to town. So we do that from config T mode by typing VLAN space, then the number. We give it a name, and then we can get rid of the VLAN. Show VLAN brief, let's show you some of that real quick. I gotta fall off my chair. We'll do 30 was. Show VLAN brief right now. Everything's in VLAN 1. All my ports 1 to 24 are all configured for VLAN 1. That's the default VLAN. If I want to create another VLAN, VLAN 10, now we see that it goes into configured -VLAN mode. And I give it a name, we'll call it VLAN of fun. Control Z, then if I do a show VLAN brief, we see that there's this now VLAN, but there's no ports in it yet. So, question? You all right?
The list, or the two different ranges that have been on the extended, that's the total number of VLANs you have.
That's your available range. So when I go in here and say VLAN question mark, it tells me I can use from 1 to 4094. So I'll pick 3096. Give it a name, John Smith.
So if you really wanted to, could you have 4,000 VLANs?
Yeah, well, no. Not with the 3750. It's limited to 128 spanning tree instances. So technically you can only have that many on your 3750, but bigger switches you can have as many as you can hold in memory. But yeah. So this one threw an error, which we'll talk about next week. Failed to create VLAN 3096, extended VLAN is not allowed in current VTP mode. VTP mode, I think, on this chapter, the next chapter. We'll talk about that in a bit. So when we want to assign a VLAN to an interface, we pick which interface we want to assign it to, and then we run switch port access VLAN, and then the number. And that puts that port on that VLAN internally. So we have Fred and Wilma on VLAN 10. This is the command that would do that, put them on VLAN 10. This command tells the switch port that I'm going to force it to be an access port, not a trunk port. It will auto-negotiate, try to figure out if I'm in a trunk port or access port. I don't like that. I like to tell it, hey, you're either an access port or a trunk port. Don't try to figure things out because they usually get it wrong. We can do that on a range of interfaces with the interface range command. Apply switch port mode access on all of them, and then switch port access VLAN 10 on all of them. Let's try that. Interface range through 10. So switch port mode access, switch port access VLAN 10. Now if I go look at those,